So today, I'm going to give you just a couple more examples over optimization so that you'll have Okay, today I'm going to give you a couple more examples over optimization so you have a little bit more information to help you with your optimization lab. So for starters, the first one that we are going to look at says that an indoor track is to be created in the shape shown and is to have a perimeter of 440 yards. I don't really like that color. Okay, perimeter of 440 yards. Find the dimensions for the track that maximizes the rectangular portion of the field enclosed by the track. So we're going to start writing what we know. Okay, first thing we know is equal to 440. We're going to write it in terms of x and y. So perimeter, I've got x and x, so we have 2x. And then we have the circumference of a circle with the radius r. If we put two semicircles together, right, we'll have a circle. So we have 2 pi r. Okay, there's my perimeter. The next thing that we can look at, well, let's go ahead and take this and we're going to solve for x. We divide everything by 2 and then we subtract the 2 pi r over to the other side. We end up with 220 minus pi r. Then what we're trying to maximize, okay, we are trying to find the maximum area rectangle on the inside. R and x, if this piece is r, then we know that this piece is r. So area is going to be x or 2r x. If we try right now to take this derivative, we're going to have to use implicit differentiation techniques. And so instead, we're going to take this, what we know about x, and plug it into that everything is in terms of r. Area is 2r times 220 minus pi r. Area in terms of r is now equal to 400 and minus 2 pi r squared. And when it comes to finding max and mins, use derivatives. So I'm now going to take the derivative of the area, which is 440 minus 4 pi r. Okay, since that is a linear function, we don't have to worry about where it's undefined. Numbers, we're going to set this equal to 0, and we're going to solve. Okay, so I end up with 440 pi r. So r is equal to 40 over 4 pi, which can be reduced to 110 over pi. Okay, we have to then make sure that this is a value. So we can either use the first derivative test or we can use the second derivative test. I'm going to go ahead and take the second derivative. The second derivative is going to be 440. Oh, excuse me, I'm looking at the wrong one. Let me rephrase. Okay, the second derivative goes away, excuse me. Okay, sorry, I'm looking here. Okay, so the 440 goes away and I'm left with negative. The reason I like the second derivative here, excuse me, pi, is because all your variables go away. There's nothing to plug in. Negative 4 pi is always less than 0, which tells me that it is always concave. Concave down looks like we're always going to have a maximum. Okay, so without plugging in, we can now say that it is a maximum. R equals 110 over pi. Okay, so now we can go back. We know where the maximum occurs, but we've got to go back and look at the question. Okay, it says find the for the track. Okay, find the dimensions. The dimensions of the rectangle we set 2r by x, 110 pi, so 2r is going to be 220 yards. So we said was 220 minus pi r. Okay, so if we need to do this, okay, 220 minus pi times 110 over pi. The pi's are going to cancel. 20 minus 110, which is just 110 yards. Okay, so here's my answer. 220 pi yards by 110 yards. Okay, so we're going to look at one more. We'll see. Okay. So it says at noon, a sailboat is 20 kilometers south of a fritter, which I think is like a bird. I don't know what a fritter is. This is fritter. We know the sailboat at noon. And we know that this distance right here is 20. And the sailboat is traveling east at 200 kilometers per hour. So right now we're here, traveling east at 20 kilometers per hour. And the fritter is traveling south. I guess I can change color here. At 40 kilometers per hour. Okay, so we're going east at 20 kilometers per hour. That's the sailboat. The fritter is moving 20 kilometers per hour. Maybe it's another type of boat. I don't know. If visibility is 10 kilometers, could the people on the two ships see each other? And when we talk about visibility, where these two things are, visibility is the direct distance. Okay, so we're going to call this D, and when we talk about visibility, okay, that's what we're talking about. We've got a right triangle here. Of all being on the same page, let's call this distance A and this distance B. For starters, we're going to use the relationship A squared plus B squared equals D squared. So we're going to try to get A and B all in terms of time. So for starters, B from the sailboat, kind of origin point, I guess, would be 20. If it's traveling 20 kilometers per hour, where time is in hours, it'd be 20 t. To find A, okay, here's where it's a little bit tricky. Okay, we want this distance right here. starting at 20. With every time that goes by, we're getting 40 kilometers closer. The way that we do this is we're going to write 20, and we're going to subtract 40t because we're getting closer, 40 kilometers per hour. Okay, so here's A and B in terms of the time. To write this, we know that distance or the visibility is always going to be greater than or equal to 0. Those cases, when we get ready to solve, right, because distance, we would take the square root, use the minimum of d squared, then we're going to set it equal to z because square root and the square are going to have the same location. Okay, so we're going to use a squared plus b squared is equal to z to find the minimum. And when we get ready to plug in, or let me rephrase, to find where the minimum occurs. When we get ready to find the minimum distance, we're actually then going to take the square root of all that stuff. Okay, so the square root of plus b squared. Here, we now know that we said a was 20 minus 40t. And we said that b was 20t. So to find where the minimum occurs, we're now going to take the derivative of z. For this first piece, we have to use chain rule, so I've got 2 times the derivative of the inside, which is negative 40, and then the inside piece just stays the same, so we have 20 minus 40t. Over here, same thing, we have plus 2 times 20t times the derivative of the inside, which is 20. And if we clean that up, if we go ahead and multiply it out, z prime is going to equal negative 80 times 20 minus 40t plus 40. So z prime is equal to negative 1,600 3,200 t plus 800 t. Okay, we're going to set 0, and we can now solve. Okay, so we end up with 1,600 is equal to 4, and t is going to end up being 2/5. We have to make sure a minimum value. It could be, so to do that, a second derivative is going to be 4,000, which is greater than 0. Second derivative greater than 0 tells me that it is going to be concave up, looks like a cup. Looks like a cup is always going to have a minimum, so we have a minimum at t equals okay. Once we find where it occurs, the final thing that we need to do and see what that value is going to be. So I'm going to say, okay, so the minimum distance, we're going to now take the square root. We've got a squared 20 minus 40 times 2/5 squared plus b squared, which is 20 times 2/5 squared. in the calculator or you simplify, you end up with the square root of 16 plus 64, square root of 80. And the square root of 80 is less than 10. If the visibility is 10 kilometers, could people on the two ships see each other? 10 kilometers apart, then the answer to the question is going to be